Swayam Prabha. Digital India. Educated India.
Yeah, so we have been talking about these mixtures, especially when we have water vapor in air, then what happens? We saw that we could define three terms. One is the dew point, the other one is a saturated mixture. We defined three terms: the dew point, the saturated mixture, relative humidity. In fact, the fourth term was our specific humidity or the humidity ratio. So the dew point is whether the vapor starts to condense, and whatever is the maximum water that the air can hold, that is like my saturated condition. So the maximum that it would hold, and if it is holding that at the given pressure and temperature, then then that's my saturated mixture. And then whatever is the actual water vapor that is there in my air to the saturated mixture that I would have, or the amount of water vapor in the saturated mixture, the ratio of these two, I will define it as my relative humidity. And because they are related by mole fraction, and because we are using ideal gas law, we can replace these mole ratios by the corresponding pressure ratios. Now, we also saw that we could define another term, the specific humidity or the humidity ratio, which was the ratio of the mass of water vapor to mass of dry air, which is there. So dry is important here. So essentially it becomes mv upon ma. And again, using ideal gas law, we can relate it to the pressures. Was the molecular weights also come into the picture here. So these molecular weights, once it is computed, and once you can compute it once and use this as a factor, we get a factor of 0.622 times PV upon PA. That's what I get as my omega. And then I can relate my omega and phi, because PV is a common term, which can be eliminated from the two equations. And I can write phi is equal to omega times PA upon 0.622 times PG. So knowing the partial pressure of the air and the partial pressure at the saturated conditions, we can find out what is my specific humidity. And we saw that when we were essentially doing this sort of an example where things are coming in at 32 degrees Celsius, 1.1 bar pressure, and a relative humidity of 80%. So what we did is went to 32 degrees Celsius, looked at the saturation pressure, which turned out to be this number. And then we know that my partial pressure of water vapor would be related to the specific humidity. So if conditions were saturated, if the mixture was saturated, then this is the pressure that water would exert in this mixture. But because my relative humidity is 90%, it is only 80%. So my partial pressure reduces by the corresponding factor. So that means it becomes 0.8 times the saturation pressure. And I get this number as my partial pressure of water vapor in my mixture. And then I can find out the partial pressure of air as the total pressure minus the partial pressure of the vapor, and then use that to compute the specific humidity. We also consider, so that's how we can find out this relative humidity and specific humidity. And then you can also look at the case. So once we know how things are going to happen, if there is moisture in there, so then we can also look at the difference in the states and the corresponding heat transfer, mass transfer that would happen if some air at some relative humidity is entering and something is leaving. And for the sake of simplicity, we assume that's a steady state condition with no work and no changes in the kinetic energy and the potential energy of the incoming and outgoing streams of air. And of course, we would be interested in knowing how much water condensation or evaporation has happened and how much heat transfer has happened in this process. So we saw that we are going to use our fundamental laws that we have already derived or that we are now very comfortable with, which is essentially balance of mass balance and energy balance. So this is now these equations or these concepts are now used in terms of in the context of the mixture. And in a mixture, we have to essentially look at the balance of air and balance of water separately because these masses cannot interchange. Of course, the energies can interchange. Energy of given by air can be absorbed by energy of water and so on. So we have only one energy equation, but two mass balance equations, one for air and another one for water. And here we are writing whatever mass is coming in of air is not changing. Whereas when we are looking at mass of water, then of course this term, because of evaporation or condensation, has to be accounted for. So that means water which is coming in is not the same as water which is going out. The difference is the one which is either condensing or evaporating. And of course, we can write out this equation by dividing it by mass of air. And then we see that this becomes my omegas in terms of omegas. So you can see that's why we have defined omegas. So typically we would, in the equations, omegas tend to appear, as you can see from both these two equations. Whereas the relative humidity is what we would like to measure because omegas are very non-intuitive and a way of writing out things. Okay, so we are essentially going to do it with respect to phi's, which is the relative humidity. So that's why we wrote a relationship between phi and omega, which was essentially given by this relationship here. So we said that if we, in a specific case, like what is given here, if you are supposed to find out if the conditions are given that air is entering at 32 degrees Celsius and 1.1 bar pressure, and it is leaving and it has a relative humidity of 80%, and it is leaving at 16 degrees Celsius, 1 bar pressure, and relative humidity of 95%, how much mass evaporation or how much water has either condensed or evaporated, you should be able to do that. And then you can find out, so by using the mass balance and then by using the energy balance, you should be able to figure out how much energy transfer would happen in this process. And of course, this is a solid example. I mean, to an extent at least. I mean, of course, all the numbers have not been put. The essential steps have been shown, and you can complete this and find out how much heat transfer per unit mass of dry air would happen in this case. So essentially, that's what we had discussed in the previous class. We will define another process, which is the adiabatic saturation process. This is essentially, there is no new idea here per se. Whatever we have covered is already, I mean, it's just an application of that. But this is an important process, so we are just doing it separately. So here is an adiabatic, and by now we know that by adiabatic we mean that there is no heat transfer that is happening. So whatever you saw with respect to that, this becomes a much easier case, and it also says it's a saturation process. So that means that whatever is leaving is at saturated condition, not more and not less. Okay, so exactly at the saturated condition it is leaving. So that's the mix, that's the process that we are considering. So that means that the relative humidity of the mixture is less than 100%, and then it has water has evaporated from a pan, and the outlet is now at the saturated, is a saturated mixture. And then whatever is the corresponding temperature of this saturated mixture, we can call it as the adiabatic saturation temperature. So that means, again, just to sort of rephrase, let us say that there is dry air which is coming, flowing over the river, and then picking up moisture. So at the end of your control volume, it is completely saturated. So, and of course, we are assuming that there is no heat transfer that has happened. It's not an assumption. If we have to actually do this process, then we'll have to ensure by design that there is no heat transfer which is happening or minimal heat transfer which is happening. So then we can define that whatever is the temperature of the air which is now leaving my control volume, I will call that as an adiabatic saturation temperature. Okay, it is essentially happening only because of the mass exchange that is happening between the air and the water pan that you have. Okay, and so this is very similar to whatever we have seen earlier. So you can write out the equations in a similar manner. So we are not necessarily going to go through it again. It's just a process that we're trying to define here. Okay, and if there are no questions, we'll move ahead. If there are questions, please let me know. So we can now define, having defined this process.
Excuse me, sir.
Yeah.
So why have we defined this particular case specifically?
Yeah. So it's like something that I mean, it tends to happen. For example, if you're considering formation of cloud, okay. So a cloud is a very special case, and of course, I'm sure in some previous class in your high school geography or whatever you would have read that the clouds are formed when hot air uh, rises from the top of hot, moist air starts to rise from the sea level, from the sea surface. And as it goes up, it gets cooled down. And at some point, it reaches a saturation. And that's where your cloud starts appearing. Right? That's a cloud level. So you can see that what we are sort of saying in this case, it's an adiabatic process because the expansion of this air, so as the air goes up, it expands because there is a reduction in pressure because of height. So the pressure reduces in the atmosphere with height, you know that. So the air expands, and we assume there's an adiabatic process. So that means it is not exchanging any heat with the surrounding, which is a reasonable assumption in this case. And of course, this expansion of the gases leads to cooling, and that leads to the increase in the saturation level. And at some point, the saturation level will become 1, and that's where the cloud starts forming. So you can see that in this process, this is a very, I mean, this is just one example where this sort of a process, it's an adiabatic saturation process. So at the cloud level, at the cloud base, your relative humidity has become 1, and that's when the things have started to condense. Your water vapor, as you go further up, the water vapor will start condensing. Okay, and at the cloud level, it's just the critical condition that you have attained. So this is just an example where you have an adiabatic saturation process, and and of course, this sort of a process do occur at several other places. So that's why we're defining it.
Okay, sir. Thank you.
Otherwise, this is a special case of whatever we have discussed earlier. So it should be easy to handle. Of course, this is when we talk about humidity. These are two important terms that comes in we encounter. One is the wet bulb temperature, and the other one is the dry bulb temperature. And we know that humidity can be found using the dry bulb and the wet bulb temperatures. So basically, there are two bulbs, which are basically means that there are classically they were mercury in glass thermometers that was used to measure the temperatures. So in one of these bulbs, essentially the one which has where the mercury is situated, you cover that with a wet cloth, and then you let air pass through this through the through the two thermometers, and whatever temperatures that you would get would become your wet bulb and your dry bulb temperatures. So, and then knowing the difference in the two temperatures, you can work out what is the humidity. So you now, by now, you have enough information to work out uh, the humidity that you would have. So you are essentially applying the mass conservation and the energy conservation equations the way we have written, and you can then find out what is the humidity that you have in your air, or you can define the relative humidity of the air. I mean, relative humidity, as we said, is a more convenient thing because you are normalizing things. You see, you can see one way to look at it is the specific humidity is mass of um, air to mass of water. So you have to always say that. It's like, although it appears to be a dimensionless quantity, it is not really dimensionless. Okay, because and on the numerator, although it's mass by mass, so it is dimensionless. But in the numerator, it is mass of dry air. You have to always make that point very clear that this is grams of water vapor to kilograms of dry air. Sometimes it is written in that manner. Because of the numbers, once you see the numbers, you will see if you write it in terms of grams per grams or grams kg per kg, it will be a very small number. So sometimes we tend to write it in terms of grams per kg. So, so I mean that's basically what I mean here. So although uh, it's a dimensionless quantity, it's a little bit. I mean, in some sense it has a dimension which you have to worry about. Whereas when you look at relative humidity is the partial pressure of water vapor in the mixture to the partial pressure of the vapor under saturated condition at the same temperature. So then here you can see that it is really a non-dimensional quantity. So this becomes a easier and a more, this is a quantity that one can explain it more easily to a layman. And of course, that's why relative humidity is used. Whereas specific humidity is much more difficult to sort of to appreciate. At least somebody who is not as well read as others, okay, or the scientific community. So that's why the specific humidity is not used. So you can see that these using this wet bulb. So we are basically now telling that how to measure these or how people were measuring it. And then we can see that using this wet bulb and the dry bulb temperatures, one can relate it to the humidity. And one could come up with the psychometric chart, which has, so this is actually a complex chart, and this is what we were alluding to last time. So there are several curves here. Let me just sort of state this and then do it in a little bit more formally in the next slide. So you can see that if you're moving along the red lines, which are maybe this line, or if you're moving along the green line, so you are moving along certain constant enthalpies or that dry bulb temperature or whatever. So you can see that so many quantities, by now we have seen so many quantities are there, or I mean, we can deal with, and these properties have to be all figured out. So you have these, I mean, once you have two properties, you get the state, but then you would also like to get what is the value for the other relevant properties like enthalpy, entropy. In this case, it may be your moisture content and so on. Okay, so you can get into so many of these other properties that you would have. And then once you have these properties, you would like to say that, okay, what path should I follow where these properties constant? Okay, and we are going to see very quickly in the next sort of chapter when we look at the Maxwell's relationship, exactly these things. So just to sort of say that you can see that this is a very complex looking chart, but once you get used to it, you can see whatever detailed calculations we did uh, with all these equations, this example that we are solving, we can do in using this chart itself without really getting to more, I mean, without needing anything more than this. Okay, so you can actually solve this entire problem without the help of any equations and just essentially using this chart. So, so what this chart has dry bulb temperature on one of the axes and the humidity ratio, which is essentially the specific humidity, on the other axis. And the chart is typically at a fixed pressure, which is usually 1 bar. This is, of course, our most relevant pressure. So when if your pressure is different, then this chart becomes inaccurate. And if it is slightly away from 1 bar, you can still use it. But otherwise, you'll have to go to a different chart, which is at the corresponding pressure that you want. So of course, so you cannot draw such charts for each pressure. So this is only for, or mostly for 1 bar pressure. And then you can see that lines of constant relative humidity, wet bulb temperature, etc. are shown, and the enthalpies of air-water mixture per unit mass of. So you can essentially use this chart, as I said, to do a lot of calculations. So I will not get into more details than these, but in principle, you can use it, and I'm sure you can, once you look at it closely, you can see all these different quantities that we've introduced, given here, and I would encourage you to solve this problem, at least the second part of this problem, where you are having conditions at 1 bar, look at what is the saturation pressure that you are getting versus whatever you're getting from the chart. And you will see that they are actually indeed very close. So I think this is what I will say for now and stop here as far as this chapter on mixture goes. So basically, we'll now look at the last topic. This is something that we have been saying for a long time, which is thermodynamics, which is Maxwell's relationships. So let me introduce the need for that, and you'll see that this is actually a very simple and an interesting topic. So we have already introduced a large number of properties: pressure, specific volume, temperature, density, internal energy, enthalpy, entropy, specific heats, whether it is a constant pressure, it is a constant volume. But the question is, how do I obtain the value of these properties? So this is an important question. Before these properties are useful for you, they have to be measured somehow, or they at least the values have to be found out. Now we know that we cannot measure something like internal energy, we cannot measure entropy, okay, and a lot of other things we cannot really measure. A lot of these other properties that we have introduced cannot be directly measured. So how do I get the values of these properties? So first of all, we realize that what can be measured are only a few handful of quantities. We can measure pressure, we can measure specific volume, we can measure mass, we can measure temperature. Okay, so these are the things that can be measured, but the others cannot be. So we should be able to. So the idea is that let us try to write out a relationship between these quantities that we can measure with respect to the other quantities which we cannot directly measure, so that so basically once we have the measured quantities, we are able to find out these other properties as well. So this is the whole idea behind whatever we are now going to do. So is the motivation clear? Is there any questions here from whatever we have said till now, whether in this part or whether from the previous part on mixtures?
Excuse me, sir.
Yeah.
So the steam tables which we were using, so those values are empirical, those values are found out by these relations, or those are experimental values.
Yes, so that would be clear once we see everything is going to be empirical. Okay, but the relationships is there, which is there from. um so basically, you are going to measure pressure, temperature, and we'll see those relationships in a minute. So ultimately, the entropy or the enthalpy that you are having is somehow related to these four quantities that we're looking at: pressure, specific volume, mass, and temperature, right? So what is that relationship and how do I get those quantities is what we are getting at. So of course the relationship is all theoretical the way we have derived it, and these theoretical relationships are going to be used to drive to obtain the value of these properties that are of interest to us. So I don't know if that answers your question.
Yes, sir, it does.
So before getting into that, let us just look at two very simple relations. We are basically looking at basic calculus. So let us say that there is a variable z, which is a continuous function of x and y. Okay, so z is a function of x and y as given here. And then I can take a dz, which is dz dx, keeping y constant, into dx, plus dz dy, keeping x constant, into dy. So this is our basic calculus. And then let us say that for convenience, I write it out as dz is equal to m dx plus n dy, where m is nothing but dz dx at derivative of z with respect to x at constant y, and n is dz dy at constant x. So by the way, I just keep on saying for both partial as well as total derivative d. Okay, so just be mindful about that. I just have this bad habit of denoting everything with D. saying everything as d. Now, so for point functions as opposed to path functions, we get that dx, dn dx is equal to dm dy. Okay, so we have now defined m and n, and we can say that if we were to take the derivative, x derivative of n and y derivative of m, then they will be the same. And we can see why, because that by taking the y derivative of n, we are essentially taking the derivative of z twice, once with respect to y and then with respect to x. And similarly, when we're taking the derivative of m with respect to y, then we're taking the derivative of z again twice, once with respect to x and then with respect to y. And we know that if the function is sufficiently smooth, then these two quantities will be the same. Okay, and therefore, whatever we have written in the previous slide, dn dx is essentially equal to dm dy. Of course, you have to note the restriction, which is that this is at constant. The first term is with respect to is at constant y, and the other one is at constant x. So this is my first very important relationship. And it's a very simple relationship. And we'll see that once we start applying it to the equations that we already know, then we start getting a whole set of very interesting relationships, thermodynamic relationships that we would have from this very simple basic calculus that we have mentioned. Any questions here? I expect not, but anyways, this is very simple, straightforward. The second relationship that we would use is what is given here, that if we take for any x, y, z, sufficiently smooth independent functions, then essentially dx dy at constant z multiplied by dy dz at constant x multiplied by dz dy at constant y is equal to -1. Now, to see this, let us say that we will consider three independent variables x, y, and z. Let us say x is some function of y and z. And of course, we can write out dx in this manner here. The derivative of x with respect to y multiplied by dy and derivative of x with respect to z, keeping constant y and multiplied by dz. And we can also write y as some function of x and z. So then what I'm going to do is I can write out this dy, and I can substitute this dy in the previous equation that I had in the first relationship. So I get dx is equal to whatever is here multiplied by dy. This was my term dy, which I'm substituting from here. Okay, so that's all I have done. And the second term in my dx relationship on my previous slide has remained unchanged. Okay, so I can now write it out as, of course, this is just algebra that I'm doing here, regrouping terms, one which has constant dx, or one which has with respect to dx, and the other one with respect to dz. And then we know that because now we can argue, what is the argument that we are going to make now? Because x, y, and z are independent variables, okay, dx, dy, and dz are independent. So that, and this is the relationship I get. So that means that the coefficients on both the sides of this equation have to be the same. So that means that here the coefficient of x on the left hand side is 1, and the coefficient on the right hand side is whatever is shown here. So that means that this term is 1, and the coefficient of z dz on the left hand side is 0, and therefore this term is 0. In the bracket, bigger bracket is 0. So that's basically what we're deducing, that we're deducing this term in the bracket, the square bracket is equal to 0. And we get the first bracket, from the first bracket, we get that dx dy at constant z multiplied by dy dz, dy dx at constant z again is equal to 1. So that means that they are inversely related. So this is something that we know, dx dy, if this was total derivative, we know that the total derivative of y with respect to x is 1 upon derivative of x with respect to y. So you can see that that relationship which applies for total derivatives also applies for partial derivatives. So here you can see that if it was a third variable that was also involved, z, then as far as that third variable is at a constant, is not changed, then this inverse relationship also applies, not just for total derivative, but also for partial derivatives. Okay, any questions till now? Okay, now I can essentially put the two results together. So we can go back and look here. So this is dx dz at constant y. I can replace it with the inverse of dz dx. Okay, so I can first take it on the right hand side, the negative term, then I get an inverse, and then an inverse. I multiply that inverse here, so it will come and sit here on this side, and on the right hand side, I will simply get it as -1. So that's what I'm getting here, and you can see that I'm getting dx dy multiplied by dy dz, and the inverse of this is dz dx, which is going to come and sit here. So this is what I get. As claimed, I get the product of these three derivatives, partial derivatives, as -1. Okay, any doubt from this basic calculus here? So if not, then we can now going to apply this and obtain our Maxwell's relationships. So we can see that du is TdS minus PdV. Now we know that all these are properties, point functions, and therefore we can write out our first relationship that we had. This is like m and this is my n. The two m and n are given to us. So you don't see that. Only after doing that, we have now realized that there's nothing but m and n. And we know that m and n are related to each other through this relationship here. Through this relationship here. Okay, so essentially we are seeing a relation of this form here. Okay, and we are saying that this is nothing but m, this is nothing but my n, and of course then they are related to each other in this manner here. You get so derivative of m with respect to the other quantity, keeping this quantity constant, ds same, is equal to the derivative of this n term, which is my p here, with respect to s, keeping v constant. And of course, there's a minus here, which gets carried in your relationship further. So that's what you get. This is my first relationship that we can get. We can also write that dh is equal to tds plus vdp. And suddenly you realize that it means that dt dp at constant s is dv ds at constant p. And this is something that we had sort of not really defined, the Helmholtz function. So if you sort of remember, we had Helmholtz and the Gibbs function. Gibbs function we had very briefly defined. We could also have defined a Helmholtz function as u minus ts. And then we can get from here dA is equal to du. I mean this relationship again, which gives me minus pdv minus sdt. And that dp here. And similarly, from the Gibbs function, we can reduce this. These four relationships are known as the Maxwell's relation. Now, what you see here, which is common in all these relations, is the quantities that get involved are T, V, P, and S. Okay, so these are the four quantities that are involved: T, V, P, and S. T, P, V, and S here, P, T, S, and V. and similarly S, T, S, and P. So what is the importance of this relationship now? Can somebody guess now?
We have two unknowns which we can measure, that is T and P, and we can somehow get S and V in terms of those.
Yeah, so that's very close. Anybody else wants to say anything here? So essentially you can see that we have four quantities out of which three can be measured. I can measure temperature, pressure, and specific volume. So then I can get the fourth quantity, which is my entropy S. And of course, it is interesting that they get related to each other in these different ways, which are all independent relationships. Okay, you cannot relate one with respect to the other, because here, so if you look at derivative of V, for example, one is derivative of V with respect to S. This is of course derivative of V with respect to T. Okay, and derivative of V with respect to S. So these are all like a derivative of V with respect to T here is there, but here it was with respect to constant entropy. This is at constant pressure. So if we were to go to a chart like what is shown here, maybe like what we were seeing just now earlier. Sorry. You can see you can, so if you are at a constant, you're at a given point, then you can move in so many different directions. One which has constant entropy, the other one would have some other curve would have constant temperature, something else will have constant pressure. Okay, so depending on which curve you are moving, so you can see that that's what these would imply physically, that your V, for example, how V is changing at with respect to T at constant pressure. So you are essentially moving along constant pressure line, isobar, and then how is the value of temperature changing along that isobar? Okay, and here you would mean that V, of course, you can take the inverse of, I mean, here V is changing with respect to S, or if you are moving with along an isobar, how is your entropy changing? Okay, that's what this quantity would mean. Okay, so you can see that it's very interesting to see that you can able to write out these relationships. And as we said in the very beginning, the whole idea is to be able to write out these relationships in terms of quantities which are measurable. And that's what Maxwell's relationship allows us to do. Now, once you have gotten a hang of this, you can see that I can write out not just these four relationship. I can write out using the two basic things that we have shown here. Uh, these the simple calculus that we have shown here in just a few slides can be used to write out a whole host of relationships. Okay, and for example, we can start seeing these relationships as well. Again, from u du is tds minus p dv, we can write out that du ds at constant v is nothing but t. Now, why is this coming from? Essentially coming from here, from this relationship here, that m is nothing but derivative of z with respect to x at constant y. So that's what we are doing here. We can say that t is nothing but derivative of u with respect to s at constant v, right? So that's what my t is. Du ds essentially becomes my t here, and d similarly du dv essentially becomes my minus p. But then you will have to hold your entropy constant. ds cannot change. Essentially, if you make ds as 0, then there's this relationship that you get. So that means you're holding s as constant, that ds is not changing, and of course du dv essentially becomes my minus p. Similarly, you can write out from using dh stds plus vdp, and this gives you this relationship here. And again, you can these are all whole host of relationships, and then you can combine these relationships the way we have said, and you can get even more relationships between them. So this is a very interesting. Very quickly, we have done this what we have wanted to do, but we can see that now. So you can start once you have. Um, uh, so, for example, once you have used your relation using your relation and your Maxwell's relationship, you have found your S. You can come to this relationship here. Here you have found your S is known by now. T is being measured. So you can start relating, you start getting your U's here or start getting your H here. Okay. Once you have your S measured, figured out from your Maxwell's relationships. So that's how you can measure your steam tables. You can draw your steam tables. On of course, format is more time consuming, so we're not getting to that. But at least you have gotten a hang of how these steam tables can be constructed. And hopefully that answers the question that was raised earlier.
Sir, but to use any of the Maxwell relations in the previous slide, we'll have to know functions of the one variable with respect to the other, right?
Yeah, correct,
So
correct. That's right. Only then you can take a derivative. Yes, that's right. So that's what I mean, that I can fitting it, and then there's a formal procedure, as I'm saying, which is sort of explained and given in textbooks. But at least now you can get a hang of. So basically, you get a relationship, how to get that relationships. Okay, so so you can see that maybe some relationships I would use for like real gases, somewhere I will use. So I basically I can integrate a lot of these things that we know from my earlier. So what is a good fit? What is a good function to assume? So we could discuss all that, but we don't have time. So then you fit those functions, take a derivative, and then you get something else. Okay. And then you keep on moving, keep on going, and then you start getting your charts. Okay. Does that answer your question? Does yeah. Sorry,
yes,
I
sir.
while you were
Yes,
saying.
sir. Okay, got it.
Sir, I think in the beginning of this slide we said that x, y, z are independent variables, if I'm not wrong.
Mhm.
So we are using for these Maxwell relationships.
Yeah.
So, okay, maybe I'm wrong. Okay.
No, but
No,
yes,
sir, no, sir, no, sir.
see, essentially why we are doing it in this form, we can relate it to again the basic thermodynamics that we have read. So we are saying that once you have two properties, right, the third property gets fixed, right? So I could take this as P and T, then my enthalpy, entropy, internal energy, everything gets fixed. So that's my Z, okay? And I can keep
Yeah.
on changing my pressure and temperature. Let us say that's my simplest set of variables or properties that we have used. I can change my P and my Z, my internal energy would keep on changing. I keep on changing my temperature, my internal energy will again change, keeping other quantity fixed. So then I can know how this internal energy is changing uh, with respect to temperature or with respect to pressure. So that's my iso constant. That's my isobar. Along my isobar, how my things are changing, or along my isotherm, how my things are changing. And of course, this is coming from my basic calculus that this relationship should be satisfied. So that's why we are doing it with respect to two variables, x and y, and we're looking at the third quantity which is of interest to us. Yeah, so that's a good question that um, the point that I had missed, emphasizing why we are looking at two properties here. So that's how it gets connected to our basic thermodynamics. Okay, any other question? So I think we have sort of covered what we wanted to cover in this course.